My name is Hiroshi Oguri. I'm the honorary trustee of the center. Welcome to Physics Colloquium this week. So this colloquium is for all the physicists on campus. And this is also a good opportunity for a particular workshop to introduce what they're doing in the workshop to people in other programs. The center, in this particular case, we'll be talking about some of the science in this collider physics workshop that is going on. Okay. And so let me introduce the speaker. So we are very happy to have Thomas Gehrmann. He's a professor of the University of Zurich, Switzerland. He received a PhD from Durham University and he has done postdoc Daisy, Karlsruhe, CERN, and Aachen before becoming a faculty member at Zurich in 2003, where he has been since then. He works on theory and the phenomenology of elementary particles with emphasis on precision calculation for collider physics. And he's a leader in this area. He is the council member of the Swiss National Science Foundation, the chair of the high energy and the particle physics division of European Physical Society. Before we begin, so the speaker is willing to take questions during the talk, but I would like to limit questions from participants of other programs and not from the Collider Physics program. If there is a participant of the Collider Physics program who has to ask a question, please save the question until the end of the talk and after people from other programs ask questions. Okay, so with that, I'd like to welcome Professor Gehrmann, and he'll tell us about precision theory predictions for high-energy physics, collider physics.
Okay, thank you very much for the very kind introduction. Now, all those of you that have been or are supervising PhD students, they will kind of know the situation that one of your PhD students commit to an important task, and then for one reason or another, they actually cannot fulfill this task. And this happens to the very best students. And you clearly know what your role as a supervisor then is. You have to bail out the student. And this is what I'm trying to do now. Pierre Monny, who was an excellent PhD student in our group 10 years ago, he unfortunately could not make it to ask me. He was scheduled for giving this colloquium, and then kind of I did not really have the choice but to bail him out as my former student. These are the moments when you start as an academic, you start to feel somewhat old, that you take over a colloquium slot of your PhD student, but this week it even came worse to me when I realized that one of my program organizers, Ludo sitting there in the middle, was actually a little while ago sitting in my undergraduate classes on classical electromagnetism. That what then makes you feel really old. Okay, but jokes aside, let me now move on to the main topic of the talk. I will try convey to you in the next hour the excitement of particle physics and the thriving for precision particle physics on the one hand on the experimental side, but even more so on the theory side. And I was told that the audience to a large part is more theory inclined than experimentally inclined, so I can promise you will also be some equations, hopefully not equations that completely take you out of the context here. And I really try to make some of the more complicated tools and concepts easily accessible to a broad audience. Okay, so when we are talking about high-energy particle colliders, many of you will have seen these event displays, and this is very essence of what we are getting out from high-energy collider experiments. So what you see here are event displays from the ATLAS and the CMS detectors at CERN LHC. as well as an artist's rendering of one of these events, which actually made its way onto the new 200 franc note in Switzerland. And what you see here in these events is actually fairly complicated structures. I mean, these lines, they represent, and these towers here, they represent all the objects that are reconstructed in a particle detector. First of all, reconstructed in the forms of energy deposits of electronic signals, and then converted into basically particle tracks, and particle tracks to which momenta and energies are associated. And you see here that you can actually have quite a huge number of tracks. So the whole situation which you get from your detector is quite a messy final state. And now we will be seeing how one can put order into these very messy final states, and actually not only bring order in there, but really turn those into precise information on the actual particle dynamics that have been taking place here. Now, for the experts, what this is basically a single W boson that is produced. This is a two-jet event, so just two jets, and we will see what jets are. And on the 200 franc notes, this is a Higgs boson K to 4 leptons. So you actually have a Higgs boson that made it there on the banknote. Now, I know that 2/3 of my audience are from astrophysics, and I can tell you there's no need for you to be envious of particle physics that they have made on the back of the 200 francs, because if you were to turn around the note, you would actually find some of the key dates of the thermal history of the early universe. And then if you go from the 200 francs to the 20 franc note, there on the front, you have quite an exhaustive listing of nearby objects in first our solar system, and in our galactic neighborhood, and then even the coordinates of a few nearby galaxies. So I think also astrophysics has been pretty well served by the Swiss National Bank. Okay, collider physics. Now, why are we actually looking at these events in the first place? We are looking at these events to learn more about the very fundamental properties of matter. And what we're doing in order to learn about this is to accelerate and collide stable particles, so typically protons or electrons, at high energies. And out of these collisions, you just have, as seen on the previous slide, get these fairly messy final states which we are trying to interpret. Now, why do we go to high energy? High energy, just by mere laws of quantum mechanics, probes very small distances. So the typical distance that you're probing goes like the inverse of the energy. So the smaller you want to probe your distances, the higher you have to go in energy. And this is one of the motivations. And then also by kind of the other key formula of 20th century physics, E equal to mc squared, the high energy can be used to produce very massive states, so states that you could not produce otherwise. But if you inject enough energy into a small region of space, there is then sufficient power there to produce new and massive particles, very heavy particles, like we've already seen on a previous slide, top quark or a Higgs boson. And these colliders, I listed here several legacy colliders as well as the currently operating LHC. They are typically many kilometer long circular tunnels where these collisions are taking place. And what you see here is that you reach energies that are in the tera-electron volt range. What you also see is that kind of the highest energy colliders are those ones colliding protons and protons, like the LHC. Simple reason that protons are much heavier than electrons, so they are less prone to lose energy by synchrotron radiation. You can accelerate and maintain them, the energy in a much more efficient manner. What you also see is that for some of the machines here, especially for the plus minus and the electron-proton machines, that among the future collider projects, not so much an increase in energy is envisaged. So you might wonder why particle physicists are planning to build the same machines over again. Now, this is precisely related to the topic of this talk. This is a quest for precision. So the new machines that would operate in similar energy ranges, they are typically designed to deliver event rates 10,000 to 100,000 times higher than these legacy machines. So really to strive for much higher statistical accuracy, much higher precision in order to really understand the fundamental dynamics of matter at a very, very high level of scrutiny. Now, we already know quite a lot about the dynamics of elementary particles at the smallest scales. And all this is very nicely described in the standard model theory of particle physics. And the standard model of particle physics, this has been established through a variety of measurements at all these legacy colliders. And basically, the standard model of particle physics consists of a total of 12 matter particles, 6 quarks and 6 leptons that are interacting through 3 fundamental forces: the electromagnetic force, the weak force, and the strong force. Associated with each of these forces is a mediator, so the gluon, photon, and then with the weak force, one distinguishes Z and W bosons, which are, however, incarnations of the same interaction. All this is then completed by the Higgs boson, which plays a crucial role in really enabling all the symmetries of the standard model to be manifest, and then in terms of these symmetries, to then give mass to the elementary particles, and to establish a hierarchy between the electromagnetic and the weak force. All this looks very nice, and at first sight, it looks like a done deal. We have the standard model theory of particle physics. It was originally established. Only about half of these particles had been found. They've now all been discovered. The latest discovery was the Higgs boson in 2012. But with this, there's still a variety of open questions. From a philosophical point of view, the standard model, although being a beautiful theory, it is not that appealing, because overall there's still 26 empirical parameters that one has to inject into the standard model in order to make quantitative predictions. The values of these 26 parameters, they look pretty much ad hoc, pretty random. Also, what you see here is the matter basically comes in 3 different copies: up, down, electron, and electron, neutrino. This is what all everyday matter is made up of. The up and down quark, they are the constituents of the proton. The electron, you give it an electron, and you have neutral atoms. All these other quarks here and all the other leptons just seem to be heavier copies of the up, down, and the electron. Why are there 3 generations? Why are there exactly 3? Why not 2? Why not 4? It's still a mystery. Also, how the Higgs boson really acts as a mediator of electric symmetry breaking is not understood in detail. And also the value of the Higgs boson mass, which can be viewed in a sense as one of the 26 parameters, to either take the Higgs boson mass or the Higgs boson self-coupling as the parameter associated really with the Higgs mechanism. Why it comes out at this value is an open question, and if you you kind of would look from a point of view of naturalness. So what would be typical scale that you would expect here for the Higgs boson mass it would actually be many orders of magnitude higher than these 125 GeV. So sitting at this particular mass range, we actually don't have a good argument for it. Also, we have seen there's three fundamental interactions now. All of you know that in nature we also have gravitation. Gravitation is absolutely not included in this scheme, and we have no way of really saying what gravitation is doing at the particle level. And then our astrophysics colleagues keep on telling us that there's more matter than the matter that we are actually seeing. All the matter that you can make up from the standard model particles, it's all electromagnetically interacting, so you will actually see it. And however, there's plenty of evidence for also dark matter being present, and there is this whole periodic table of the standard model actually does not provide any good candidates. So one of the main objectives of present and future particle collider experiments is the search for physics beyond the standard model. This goes in along two broad directions, namely directly that you really try to produce new particles, and this clearly can only go basically only go through higher and higher energies, and alternatively, as an alternative to these direct processes, you can't reach sufficient energies to probe a new phenomenon. You could also look for very small imprints of new phenomena on precision observables. That this whole standard model theory, it's a whole theoretical framework, and we will see how to turn predictions of the standard model into numbers throughout this talk. And then your standard model predictions can confront them with sufficiently precise experimental data and look for small deviations that could be first imprints of new phenomena setting on. Okay, now the main part of the standard model that this talk will be concerned with is the strong interaction. Now, the strong interaction in the framework of the standard model has its own theory, quantum chromodynamics, which is the theory of the interaction of quarks, which are the matter particles, the strongly interacting matter particles that are constituents of protons and neutrons, and gluons, which are the force carriers. So the gluon to quantum chromodynamics is what the photon is to quantum electrodynamics. Now the gauge structure of this theory is more complicated than in quantum electrodynamics. Quantum electrodynamics is an abelian theory. Here, the underlying symmetry is a non-abelian symmetry, which leads the gluons also to self-interact. So photons, they basically, by superposition principle, they can pass right through each other, whereas gluons will interact with each other. That has a very, very important consequence, namely a strong running of the strong coupling constant, a very pronounced energy dependence of the coupling constant of QCD. And you see this here. This is taken kind of from the annual data book of particle physics, the particle data book. You see here that as a function of the energy scale, strong coupling constant actually changes wildly between here 1 GeV, so that's around the proton mass, to 1 TeV, which is the typical energy of an LHC process. You see it actually covering nearly 1 order of magnitude. And while this is on the one hand kind of an interesting observation, it also has extremely important consequences. If you remember that high energies correspond to small distances, also means that low energies correspond to large distances. At large distances, we see here that the QCD coupling is really growing very, very strongly. If gets large, that means that in order to pull apart two quarks here, you actually have to inject more and more energy. You're basically climbing up here, further you pull them apart. And by pulling apart these quarks, it's then not like you pull apart an electron and a positron. At some point, you've reached their binding energy, and they will just exist as free particles. But here you need to inject, the further they are apart, the more energy you actually need to inject. As in electrodynamics, the further they are apart, the less you need to inject to even move them further apart. That then means that you're storing more and more energy in the force field in between these quarks here. And suddenly you've stored so much energy in this force field that's enough by E equal to mc squared to create another quark-antiquark pair out of the vacuum, actually to have the charges then still confined. So this means that you cannot pull hard enough on a bound state of quarks, pull them apart to become free quarks, because at some point they will just have enough energy to color neutralize, to recompose, and to form two strongly interacting bound states. And this means that quarks and gluons, they're only observed in bound states. And we call them hadrons, the proton, neutron, ions, and so on. High energy end, this is where all the colliders are sitting. Small distances, IFS gets small, and we're speaking about asymptotic freedom. And whenever you have a small coupling parameter, actually do perturbation theory. Now here, on the one hand, it's a nice illustration of the qualitative behavior of the strong coupling constant. On the one hand, there's plenty of data on it, and I would like you to remember here, especially these orange points, where in the course of this talk, I will try to explain to you what actually goes into extracting these points here from data at the very highest energies. Okay, so QCD, we've seen it's a theory of quarks and gluons. We are never ever going to see quarks and gluons in our detector. Theory describes partons, quarks and gluons. The experiments will always observe these bound states, because quarks cannot be free particles, gluons cannot be free. And they don't observe single hadrons. Typically, they observe a lot of hadrons. I mean, here you have plenty of tracks, plenty of energy deposits. And what experimentalists then do in order to bring structure into this is to cluster nearby hadrons with a more or less common momentum direction, so that are pointing to the same calorimeter cells that are having nearby tracks and so on. And this underlying to this is a fairly clear prescription, a so-called JET algorithm, which is a recombination procedure. So how do you take all the form momenta that you reconstruct from your individual objects here, from your individual hadrons, and assign to it, reconstruct from it a common jet momentum, a common momentum of this co-moving cluster. And then you do the same thing with your partons. Also, if you have your QC partons, your quarks and gluons, you describe in your theory, you then look at the same final state. You look at co-moving quarks and gluons and let them form your jets. And it is at the level of these jets that you're really talking about final state objects in your event. And this is also at the level of the jets where theory and experiment are meeting. Now, confinement has another important consequence. The proton itself that we're colliding, bound state of quarks and gluons. And now, if we add two protons at very high energies, then asymptotic freedom comes into play, and we can basically view a proton as a statistical superposition of quarks, gluons, also antiquarks, and so on. So you have a statistical description of your initial state, of your initial colliding proton that you can say, okay, with a certain probability, I see inside this proton say in this case an up quark, taking a fraction x, so that's 1/10, 1, so some fraction x of the incoming proton momentum. This statistical description then allows you to describe this collision not as a proton-proton collision, but theoretically describe it as a quark-gluon collision. And here, kind of, we have an example for a Feynman diagram description. Time would be running from left to right, and the space coordinate is kind of on the vertical here. And you have kind of your protons coming in. You just pick out a gluon of one proton, a quark of the other proton. They scatter on each other. In this case, they radiate a Z boson, and this is recoiling against the jet. And with this, you can actually theoretically describe cross-section for producing a certain final state in terms of a theoretical calculation of your interaction cross-section, then multiply it with these statistical distributions for the partons that you have in your colliding protons. Okay, so with this, we're kind of ready to confront theory with experiments. So theory kind of allows you to compute these parton-parton scattering cross-sections into a final state made out of jets that still are made out of partons. And then you compare this with jets made out of hadrons, and you transfer it to a proton-proton collision by these parton distributions. Right, and this is where theory and experiment then can meet. In this single figure, the Atlas collaboration tried to really make a cartoon picture of all the standard model reactions that they are measuring, and kind of for you to navigate your eye. The blue line here indicates what the LHC will be producing per second on a good day of operation. And here are all the different final states. And at this 1 second line, for instance, you have top quark pair production. There's one top quark pair produced every second, and it's a little less than one Z boson produced every second. There's perhaps 10 W bosons produced every second. And this already tells you that these standard model production cross-sections, they come with enormous statistics. We are no longer statistics limited. We are perhaps systematics limited. We are reconstruction limited. And not only you get kind of the final state, say, the W boson, but also get more complex final states involving a W boson. So in this column here, if you go down, each of the next measurements, W plus 1 jets, 2 jets, 3 jets, 4 jets, 5, 6, even up to 7 jets. All these final states have been measured. Distributions in these final states have been studied. Then you start confronting theory with data and start looking for deviations in all these observables. We will be particularly concerned about is now those cross-sections that have very large event rates, so that are not statistically limited, not even systematically limited, but that are actually limited when you want to confront them with standard model predictions that are limited by the quality of the underlying theory. So how good can we predict these precision data? And what people observe there is that for many of these cross sections that are measured sometimes to a percentile or by now even per mil level, that the theory accuracy is still in the range of around 5% or so, and that is a clear playing the ball into the field of the theorists, that theory needs to come up with better predictions. Now, we are always in the region of asymptotic freedom there, so perturbation theory applies. We have seen that a lot of the interesting observables are those ones that involve finite state jets. Then we should see what perturbation theory actually tells us about jets. Now, perturbation theory is an expansion in the strong coupling constant. In the strong coupling constant, kind of the leading order description of a jet is quite a poor description. Namely, you model each jet by a single parton. So all these objects that contained multiple tracks in these event displays, they actually are identified with a single parton. next to leading order in perturbation theory, you kind of per order, you allow for one extra parton. And that means next to leading order, you have 2 partons in the jet. Next to leading order, 3 partons. There you start kind of building up this cascade. You see that that your description of the jet, your modeling of the jet, will get more accurate with each increasing order. It's one extra parton. I mean, I've drawn this here as a real parton radiation. We can also have vertical parton exchanges, so that only internally in the dynamics of the process, the parton is exchanged. That would also always give you one more order. Now, of course, this is kind of the rigorous perturbation theory approach. Particle physicists have also devised approximate approaches to describing jets, so-called parton showers. We don't take the full exact next to leading order dynamics, but you try to identify what are the dominant contributions, and then you exponentiate these dominant contributions. So say, okay, the radiation of 2 gluons is the radiation of 1 gluon squared in whatever metric. And what you do there is you can simulate multiple emissions. You lose the quantitative accuracy on. Now, the state of the art for any process is next to leading order. So, owing to a substantial body of work that to quite some extent has actually been initiated by Kostas Papadopoulos, who is sitting here in the front row with his CAD tools package. Next to leading order calculations can now be done in an automated manner, in the sense that you basically tell your computer what process you would like to have, and then it computes you the next to leading order of predictions for it. This is only possible in the form of community effort and through a huge amount of standardization, namely that all the different ingredients that go into such a calculation, they have extremely well-defined interfaces such that different people can work on the piece of the calculation that they're really expert on. And then at the end, you can put it together with other people's contributions in order to have a highly automated framework. Now, this even combines then with parton showers such that one has full event properties with next to leading order accuracy, even on differential cross sections. However, in terms of perturbation theory, next to leading order is still not precision physics. Its accuracy is somewhere in the range between 10 and 30%. So that's still a pretty huge uncertainty, and therefore we would like to go higher in perturbation theory. And this is what the remainder of the talk will largely be about, how to go to the next order in perturbation theory. And that's really a template for going to higher orders. And there I would like to walk you through all the ingredients and the anatomy of a next to leading order calculation. And next to leading order, we've seen we have 2 extra partons compared with 1 level process. Now, these 2 extra partons, they can come in different incarnations. They can come as purely vertical exchanges. Now here, I've drawn diagrams that are relevant for the process proton-proton to 2 jets. So you have 2 gluons coming in here, 2 gluons coming out, and we are next to leading order. So we have 2 layers of perturbative corrections. The bond level would just have gluon exchange here middle. Now, give it 2 more gluon exchanges. We have 2 closed loops here. It's purely vertical corrections. And they appear at this order, but they're not the only contribution appearing at this order. You can also have 1 loop corrections through a single emission. So this now doesn't have 2 gluons in the file state, but 3 gluons. Or you can even have file states where we have 4 gluons in the file state, always then requiring that in our file state, when we cluster together the jets, that these extra gluons, they arrange themselves in momentum direction such that the file state we only see 2 hot jets. Now, all this is very nice. I can draw the diagrams for you. I can even write down the expressions mathematical expressions for all these scattering matrix elements. However, if I try to evaluate them, actually realize that it's not so easy to get numbers out of these. It's most obvious in the two-loop matrix elements. I mean, here what I have to do is to integrate over all possible values of these loop momenta. And what I see then is that this basically comes out to be infinite. And so we have here explicit poles, especially from infrared momentum regions. So when this gluon here takes a very, very low momentum, and also this gluon takes a very, very low momentum, actually see that, that this integral here explodes. So you need a regulator, and this regulator then translates into explicit infrared poles. Now, same already holds true at one loop, get explicit infrared poles from the loop. But something new is happening here. This extra gluon here, I mean, we see 3 gluons in the final state, but only want to have two jets reconstructed. So one of these gluons, say the middle one, is totally unconstrained, can get to very, very low energies, or can become very, very collinear to one of the other gluons. That is another source of singularities. So in these one-loop matrix elements, we also have so-called implicit infrared poles, which we only get after doing the jet clustering and integrating the phase space. Tree-level, there's no loops. So the tree-level matrix elements, they are finite. We have way more particles than we require jets. We can actually afford to have 2 of these particles basically vanishing to arbitrarily low energies. This, again, gives rise to infrared pole configurations. So although we just, quote unquote, need to evaluate these different scattering matrix elements, they're not that easy to evaluate because a priori all of them are infinite. Let's see how we deal with these infinities and how we deal with the evaluation of these matrix elements. One of the key ingredients of higher order calculations are virtual corrections. Here, taking as an example this two-loop amplitude, the way we would write this down would be looking like this. You have the integration measures for the 2 loops. So this loop L, this loop K, and then you have propagators that denominator factors. So each propagator that is connecting 2 vertices here would appear as the denominator factor. And then you have some numerator factors that basically come from the Feynman rules of gluons interacting with each other. And this is generic structures. You have propagators in the denominator, scalar products in the numerator. Some of them are raised to higher powers, higher or with integer powers. What you're using here, you're not integrating in 4 dimensions, but you're integrating in symbolic d dimensions, which is called dimensional regularization. We move away 4 dimensions. And there are 2 challenges associated with this. The algebraic complexity, so these expressions can become extremely large, and not only very large, but there's also many of them. So you have very, very many of these 2-loop integrals that you need to compute. And there, this algebraic complexity, you will have to overcome it by reducing the very large number of different integrals that appear in such a scattering amplitude to a more limited number of integrals that you perhaps then manage. And this more limited number, you call them master integrals. Now, still, if you come down to a smaller number of integrals, you're still left with a few integrals to do. And that's the other part of the complexity, really the analytic complexity, that you have to evaluate these master integrals either analytically or numerically. Now, there has been an enormous progress in both these directions. In order to reduce the large number of different integrals that one gets by writing out these Feynman diagrams, one can make use of basically Gauss's theorem in dimensional regularization, namely that the integral over total derivative of function vanishes in dimensional regularization, and then you can construct different functions out of your set of external momenta, your set of loop momenta, and then in here all these propagators and scalar products that you're initially interested in. And what you see here is that carrying out this differentiation will give you a large system of linear relations between integrals with different powers on scalar products and on propagators, and these very large systems of linear equations. And there we're literally talking about millions of equations. You can attempt to solve them in a closed form, but the real game changer was to introduce lexicographic ordering that you can say this integral is more complicated than that integral, that you can really order all these integrals by degree of complexity, then say, okay, I take my system of equations and I solve first for the most difficult integrals such that I'm only left with the most easy integral. There's a lot of technical development, to a large extent also pioneered by Andreas von Manteuffel, who is equally sitting here in the audience, to make this large system solving a lot more efficient. Right, with this, we still have not computed the integrals, just down to a smaller set of integrals. These are still typically infrared and or ultraviolet divergent. The ultraviolet divergences we are not too much concerned about. They are removed by renormalization. It's a standard procedure, but we still need to evaluate these divergent integrals, which means separate off the divergent and the finite parts. And kind of the most bold approach to this is a direct numerical evaluation, that you say, I look at an appropriate parameterization of my integrand and of my integration measure, and then I partition the integration space such that into non-overlapping sectors, such that at the edge of each of these sectors, I only have one and only one type of divergence. And then I do a Laurent expansion, and then dimensional regularization tells you how to get your poles, namely such a factor of 1 minus z to the minus 1, which diverges at z equal to 1. This then translates into a delta distribution times the 1 over epsilon pole, plus this expansion in distributions. And then you just go ahead and numerically integrate all these sector integrals. This is kind of the brute force approach. It is broadly working, but it is highly inefficient and time intensive. So one would actually like to do better, and there's a variety of methods available to do this better. There's kind of direct analytical evaluation where you go to the appropriate variables and then come out with fairly complicated integrals, and fairly often, especially in simple low multiplicity cases, you can perform this direct evaluation. A lot more powerful is an indirect method, and the indirect method is pretty closely related to the idea that we have here, namely that you differentiate the integral by differentiating your integrand. They can differentiate your integrand with respect, say, to internal mass or to some external scale. And after differentiating your integrand, you clearly change powers on scalar products, powers on denominators. Then you have the integration by parts identities, and you can get back to your original integral. And so you have expressed the derivative of your integral as some multiple of your original integral, nothing but a differential equation. You can write down, without explicitly integrating your integrals, you can write down a differential equation for them. And then, by applying the integration by parts identities, you get systems like this. Now, this is a very simple example. I mean, this is a two-loop vertex function with a massive particle going into another massive particle and a massless particle. Here I have the differential equations in the two masses. This is the mass on here. This is the mass on here. You see a very simple system of differential equations, which already has a fairly nice feature. Namely, remember, we're doing dimensional regularization, so we're expanding around d equal to 4 dimensions, 4 space-time dimensions. And you see here, the integral itself is suppressed, this factor of d minus 4, on the right-hand side. So this is a system of differential equations that you can actually iteratively integrate by just inserting the previous order in your expansion in dimensional regularization. For those of you that like to play around with differential equations, you will immediately see that this system of differential equations are actually the Gauss hypergeometric differential equations, and this integral is expressed as a Gauss hypergeometric function. So then compute your integrals by integrating these differential equations and subsequently matching to the boundary conditions. However, the boundary conditions, they are then much simpler integrals. For instance, what we would do here is at the vanishing point of P3, we could easily evaluate this integral with the other methods like the Feynman parameter. Okay, so two-loop matrix elements using these methods of integration by parts identities of differential equations have been computed for a variety of processes. So all the 2-to-2 processes are known. A lot of the results on 2-to-3 processes, so on a higher multiplicity process, have been obtained to a large extent owing to work of people here in the audience. Herschel, Matthew, René, and Andreas. I hope I have not missed out somebody here now. So a lot of these results are now available and are ready to be actually used in calculations. Now, all of these results are, however, still infinite, and they are only part of the story, because in order to get meaningful numerical predictions out, they need to be combined with the real radiation, single real radiation at one loop, and double real radiation at tree level. And the infrared singular behavior of these objects, this is pretty well understood. And for instance, at tree level, you know that what can happen if both these particles get low energy, so they become soft, or if one of them becomes soft, the other one goes collinear, it's one of the hard particles, or also if three of them simultaneously become collinear. In all these configurations, we actually know what the singular behavior is, but we now, for a more complicated process, to have a method to extract all these behaviors from our processes and to actually numerically numerically regulate them in such a way that we can sensibly evaluate them. From the structure of it, and this is now the full structure of our cross-section next to leading order. Here we have the double real radiation, we have the vertical single real radiation, and here we have the two-loop contributions. Now all of them are infinite. If I would like to make them finite, I need to cut off in one way or another all this real radiation behavior, all the double soft limits and all that. And if I cut this off, I of course need to add it back again. I also need to cut off the single unresolved behavior at one loop. Need to add it back again. And there's another property which is specific. Hadron colliders, there's some level of initial state radiation. So your parton, before actually entering into the collision, can have singular initial state radiation, which I also need to take account of. Now, this formula looks very complicated. I don't expect you to even try to understand it. Rather, I would like to discuss what one is doing on a toy example. Namely, what we are doing here is basically doing this type of integrals, this type of limiting behavior. This is a vertical correction. I've already made all my singularities explicit. This is a real radiation correction. It lives on a higher multiplicity phase space over which I'm integrating. And you can see that kind of at the end point, x equal to 0, these two will properly match each other's singularities. Broadly speaking, there's now two ways of evaluating this integral. So here we want to evaluate real radiation plus vertical correction. And we clearly see that the problem is with this real radiation integral now we basically have two possible approaches, two types of approaches. One is a slicing approach. We say, okay, we don't integrate right to zero at this one develops a singularity. We stop at some small parameter before, then below this parameter, we actually use an approximation to the integrand. And we use an approximation to the integrand that has the right singular behavior and that allows us to actually cancel, isolate the singularity here, cancel it with the virtue. And what you see here is that this only approximate because I did not subtract and add back in exactly the same thing, but by making delta sufficiently small, this is as good as it can get. This is a very, very this is the basis of very, very successful method. The alternative to this is a subtraction. I find an approximation to this function here is still sufficiently simple that I can integrate it. And here, clearly the approximation to f of x just be f of 0, one-dimensional integral, and I can easily do this. Then I subtract and add back the same thing. I see that I have I also have a perfect cancellation of these of the singularities here, and that I now can do this integral here numerically. And also in terms of subtraction, there's a variety of methods that have been developed. I mean, here the one-dimensional example, you don't fully see the complexity of the real thing because here your f of 0 does not depend on any other variables. In a realistic setting, I mean, your real radiation phase space would be perhaps 10-dimensional, and you want to regulate here in one variable while introducing here a function that depends on also on 9 other variables. Okay. And there's various ways of constructing these subtraction terms. I will only briefly cover the method that our group has been pioneering, which is so-called antenna subtraction. And this starts kind of from a physical picture, namely that we go through our process, we look at all the possible combinations of partons, and then ask, in between these two pair of partons, what unresolved radiation can happen. And what essentially the unresolved radiation that can happen in between two hard partons is that you emit either a low energy parton in between them, or that some parton becomes either collinear to one or collinear to the other. You have collinear on one side, collinear on the other side, and soft. Then you try to find an interpolating function that is interpolating between all these three limits. They're kind of the simplest function that you can find are these current decay matrix elements that you postulate some current that does not need to be a physical current that decays into three partons, and you normalize it to with the same decay two partons. All this leads to a very nice factorization of the phase space that actually allows you to analytically integrate. And this is this piece here, analytical integration, analytically integrate the subtraction. Now, this is next to leading order. Next to leading order, you can have even two partons in between these two hard partons that become unresolved. And you can have this not only at tree level but at one loop. All these combinations you can then integrate analytically, and in part, some of the work that Pierre Monny has been doing during his PhD thesis was actually understanding these structures and constructing these types of subtraction. Now, with this, you can then actually go into a numerical program, and different groups have different numerical programs that are implementing these next to leading order calculations. And basically what these programs are doing is generating events one by one, generating a kinematical configuration of pi state particles, like an event that you see in a detector. And owing to all this rearrangement of the infrared singularities that we are doing, we are able to have numerically finite expressions for all the contributions. And then you start basically generating your events, and you do exactly the same thing as is done in an experiment. Analyze these events, you bin them into distributions. reconstruct jets, you apply cuts, and so on. And we have a variety of processes. A lot of the processes that you saw, the staircase plot by Atlas, we have them implemented in there. This does not come for free. We are talking about typical runtimes in the tens of thousands to hundreds of thousands of core hours in order to get sensible prediction. Now, with this, let me now turn for the last 5 minutes to physics predictions. And there I have selected 2 class of examples for you. One is photon plus jet production. Now, photon plus jet production, this is, if you look at the Born level process here, it's a very simple process. A quark and the gluon scattering give you a final state of a photon, and here an outgoing quark, which is a jet. And this process is a very large cross-section. It's particularly interesting because it offers you a sensitivity on the gluon distribution in the proton. So this probabilistic distribution of gluons in the proton is potentially one of the best measurements. Now, all this would be very nice and easy if the devil wouldn't be in the details. And the devil here is in the details, namely a photon is an object that is notoriously hard to identify at a Hadron Collider, and you can actually have the photon not only produced kind of in the hard interaction, but you can have it produced at a much later stage when already this rearrangement of partons to hadrons is taking place, suddenly emit a photon. What makes things even worse is that you, instead of producing a photon, actually produce a neutral pion. Dominant decay mode of neutral pion is to 2 photons. Now, this is a very, very highly energetic pion, so it's strongly boosted in the forward direction. These 2 photons actually are seen only as 1 photon signature. So you actually need a photon isolation, and you start getting sensitive on the details of the sterilization procedure and so on. But still, you're then able to precisely replicate the experimental setting of this measurement, which is including photon isolation procedure, all the selections, and so on. And you're actually able to make quantitatively very reliable predictions. Now, previously available next to leading order predictions are indicated here in blue, and the newly computed next to leading order in red. What one sees is that the quantitative accuracy of the next to leading order goes well beyond the uncertainty that we had next to leading order. The red band is considerably smaller than the blue band. And also in some of the extreme regions of the kinematical distributions, where you get a much better description of the quantitative behavior of the data. So really, these distributions, they are sensitive precisely on these multiple radiations that we are including by going to higher orders. So they are these regions here, also out here. They're really sensitive. They're really sensitive to the precise density dynamics, to multiple radiation, and so on. There, it's next to leading order is really the first order, where one sees this being correctly reproduced. Okay, now turning to precision measurements, and here I shamelessly borrowed results from René Poncelet, who is also sitting in the audience. He and his collaborators, they have recently computed the 3-jet production and related event shapes at Hadron Colliders. Now, what's an event shape? If you have 3 jets, they point in 3 directions, they have 3 energies. Out of the kinematical variables, you can compute correlations, like correlations, the opening angle, the distributions in the opening angle of 2 of these jets weighted by energies. And these event shapes, they are highly sensitive on the underlying dynamics. And they used a different method. They didn't use antenna subtraction, but they used residue subtraction, which is another subtraction method for their numerical implementation. What you see here, kind of again with the same color coding, putting next to leading order in blue, next to leading order in red, is that now the uncertainty of the predictions comes to the level of the uncertainty on the data. The data are the black are the black bars here. These are highly precise data uncertainties in at the level of 2, 3, 4% or so. And you see that the shape of the data is well described. Normalization of the data is also broadly well described, sometimes not perfectly well described. And what you can do then is, okay, here I have my theory prediction. The theory prediction has been done with some setting of my standard model parameters. Recall that we have a total of 26 parameters that are there in the standard model, and we don't know all of them particularly precisely. Now, the dominant parameter that enters into here is the strong coupling constant. So what the Atlas collaboration then has done with this calculation is to use each of these individual plots, each of these spins, as a separate measurement of the strong coupling constant. And this is, here the points are in blue. These are precisely orange points that I had at the beginning of the talk. These are the highest energy measurements that were ever done of the strong coupling constant, basically out of combining these 3-jet event shapes with a precision calculation and then measuring the parameters in this calculation. Okay, and this is already the outlook towards ultimate precision. We've talked a lot about next to leading order. One can even go one order further in this, and there we're really starting to get to sub-% level precision or beyond. And quite a bit of this can be done through upcycling of lower order calculations. Namely, what one can do is, if I say, look at Z-boson production, and Z-boson plus jet production means that the Z-boson needs to recoil against something, needs to recoil against the jet. The Z-boson produced in association with the jet will always be at transverse momentum is not equal to 0. And that means that I can use my calculation for Z-boson plus jet production as an ingredient of the Z-boson production without a jet, one order higher. This is precisely the idea of some of the slicing methods, and we use this idea again together with Pierre Bonny, who normally should have been standing here in front of you, to actually make very, very precise calculations for single lepton distributions in Z-boson production that will go then into the next generation of HC analysis. With this, I am through with my talk. I hope I could convince you about not only the relevance, but also the excitement and the technical challenges that are associated with precision calculations. And with this, I close here and am open for questions.
I think we can take some questions from non-experts first.
Don't be shy.
Yes, the person from. Yes.
I think it should talk and instead particularly about work of your group. So I have a question regarding your things that consolidate and you showed for once. In particular, the open problems in this standard model, particularly for instance of the further understanders and the two generations. So my question was if I think there is a considerable effort on the desk and that view down simply aspect based on underlying theory probably we know and then so the could please comment on that yes
Well, you
ideas and whether they can be tested right
you have a variety of approaches kind of embed the standard model into a larger theory, because they kind of weigh all the experimental evidence that we have. They tell us one important message, namely that the standard model is the correct theory to describe the dynamics at the energy scales that we could assess so far. And so that means that any larger theory needs to have the standard model in a sense as its low energy limit. So you're looking into embeddings, and the way you're embedding this into a larger theory is postulating further symmetries or postulating larger number of dimensions, postulating broader theories. Now, if you then unravel these theories to the energies of the standard model, what is then going to happen is that you can look at interactions, at scattering matrix elements that involve as external states only the standard model particles, because these are the only ones that we can create and observe at colliders, but that potentially lead to new interactions, to fairly small changes in the interactions of known particles. Now, this goes under the name of effective field theories. Basically, what you're doing there is you go by dimensional counting, that you look what are the different combinations of fields. So this can be matter fields, can be gauge fields that I can write down up to a certain mass dimension. The standard model is basically containing everything that you can write down up to mass dimension 4. And mass dimension 5, you can actually only write down a single combination of standard model particles, which is some combination of neutrinos. At dimension 6, you can already write on a vast number of combinations, but then dimensional counting tells you that they need to be accompanied in their interactions, in their Lagrangian, with an inverse power for mass scale. This is where you start doing the precision physics. I mean, all these all these larger theories, their effects at low energy, so at the energies where we can do the measurements, it will always be suppressed by some large mass scale, and that then means effects will be small. Can be percent level, can be sub-percent level. In some of the observables that people are looking at, especially in the flavor sector, limits that you get on kind of the size of these effective interactions. They range already now in the hundreds of TeV, thousands of TeV range, simply because your data are so precise, your theory is so precise, it is so extremely constraining. So what you're effectively, in terms of measurements, what you're looking at, I mean, you're not going to measuring a theory, but you're going to be measuring imprints of a certain theory in the form of strongly mass-suppressed unconventional interactions. And then building on this, I mean, like in the structure of any scientific revolution, all these mass-suppressed effects will be individual, each by themselves will be an anomaly, out of which one then tries to reconstruct a theory or to mirror it onto some existing theory. I mean, there's very successful models embedding the standard model, like the minimal supersymmetric standard model, like some low energy limits, even motivated by string theory or large extra dimension models. All of them will give rise to some mass suppressed effects. Is these anomalies that one is then looking?
I'll take your question. Yes, sir. It's one behind. So, I have maybe a simple question, but it came to me as you were on this slide, actually. Why are protons and neutrons a combination of 3 quarks, not 2 from 4?
Okay, this has to do with the structure of QCD and with the charge structure. And initially, kind of the postulate that that protons are bound states of 3 quarks was a postulate that was made out of spectroscopy. So people started not by observing quarks, but people started by observing hadrons, bound states, and then, and this is 1950s, 1960s, they tried to put some order into this, so to group them by properties, and properties, this can be mass, this can also be lifetimes, this can be specific decay modes, and you try to arrange, first of all, these particles, the hadrons, according to their properties, and then try to see how do different of these objects are actually talking to each other. How are they related among each other? What is the underlying symmetry that governs these different objects? What one then found is that they can be most economically described by bound states of three quarks. This have the observation of the bound states. This then immediately went into the construction of QCD as a theory, and QCD as a theory is constructed in such a way that basically the charge assignments that one gives in QCD, like the plus and minus charges that you have in electromagnetism, charge assignments in QCD, they come in three variants. And sometimes they're called red charge, green charge, and blue charge, in such a way that group theoretically you can construct charge neutral states, either by combining one charge and one anti-charge, or three like charges. So the origin is spectroscopy of this, but the spectroscopy led to a postulate, and the postulate is then realized precisely in this non-abelian form of the theory. You have not one copy of your charges, but three copies, and then the three copies allow you group theoretically to construct precisely three bound states of three quarks as the neutral states.
I think we Y and G's are waiting for us, but because there is an urgent question, we can take one. Right, you have the question?
It definitely wasn't urgent, but I can ask now.
Yeah,
Go ahead.
Definitely not.
We need to wait for
No, I was a student. I actually was a member of Atlas, and I remember doing combinatorics with the data. A jet was a jet, and then there was no further like definitions beyond like the angle of the jet. But but of course it's made out of partons, and like very complicated thing. And I imagine from the other plots that you've shown, there's an inherent variance that comes probably from a whole range of things that might contribute to a single jet event. So I was wondering, with these predictions and program, first, will there be a variance that remains to the theory prediction at the highest order you go, given the fact that it is actually a complicated thing made up the partons and so on? And if so, then is it possible to like maybe mass bin or energy bin to learn even more, like go beyond just a initial jet?
I mean, there's been enormous effort. There's not a short answer to this, and so that I should actually be repeating the question. So the question is that by going and beyond the jet as a single entity, whether we can learn even more. And there's enormous efforts going on in the understanding of jet substructure, and in making better jet definitions. So jet definitions where theory and experiment can talk to each other even more closely. Is the jets that we're having here, there's always still some level of ambiguity. One should perhaps be more specific. I mean, both the place where theory and experiments are meeting is where the experiment corrects to particle level, essentially. And from your experience at Atlas, you know the particle level definition is perhaps 2 pages in a document which has even more definitions and so on. So there's not an easy answer. It's an extremely active field of research.
Thank you very much. So let's thank the speaker again.